Hello, everyone, and welcome to a new session of your channel, Basic Engineering. If you remember, we stopped at analyzing rigid bodies in 2D, and we said we had three equations of equilibrium: summation of the forces in the x equals zero, in the y equals zero, and then the rotation, which was about the z-axis equals zero. Today, we are going to go over the supports in 3D. Okay, so um, again, let's say supports or support reactions in 3D for rigid bodies. First of all, before, like when we were discussing the supports in 2D for a rigid body, first we had to think about how many equations of equilibrium, because I want my rigid body to be statically determinate. Okay, so I cannot use more support reactions than I have equations, or else using statics alone, I won't be able to determine the magnitude of each of these support reactions. So let's think about it. First of all, a rigid body is more constrained than a particle, because at the particle, all the forces intersected at a point, and for the particles, we had three equations of equilibrium, so they stay correct, right? Summation of the forces along the x-axis equals zero, summation of the forces along the y-axis equals zero, and summation of the forces along the z-axis equals zero. But we know now that it's not enough to restrain the body from moving in one direction or another, but now it also cannot rotate. But in 3D, notice in 2D, we had only one equation of moments, which is the moment around the z-axis should equal zero. The body cannot rotate about the vertical or the axis perpendicular to the plane of the rigid body. But if we have a body in 3D, it really can rotate about any axis. So we won't have two, but we'll have three equations of equilibrium, which are the summation of the moment about the x equals zero, summation of the moments about the y equals zero, and the summation of the moment about the z equals zero. So generally speaking, we will have to worry about six, we will need to use six support reactions. Not necessary. Sometimes we'll see why. Sometimes we need less than that, but we cannot have more than that. Okay? Most of the time we'll have that many. So in order to look at the different types of supports, there are many supports out there, but I picked few of them and maybe I can discuss a little more. So let's look at that. I showed you four here, but we probably can get at least half a dozen more. The first one is not really a support, it's a smooth surface. So your support is resting on a smooth surface. Like if you have, a marble floor and you have a chair sitting on it, you can push it in any direction, but you cannot push it to crush the floor and move to the lower floor, right? So if that's the X, that's the Y. Yeah, it's free to slide in any direction, and you would love it to slide so that when you want to clean, you can move your furniture easily. In fact, it moves in the X or the Y as you want, but it cannot move along the Z. Hence, there would be F sub Z or R, let's say R for reaction, R sub Z reaction. So a smooth surface, or even if I have a ball here or a roller, it can slide like, when you attach something to the some casters or something to the bottom of your heavy furniture so that you can move them easily. So something like that. Um, okay. So that's a smooth surface. The second most common and easy one is called the ball and socket. A ball and socket, as I always told my students, you have two of them in your body. You have your shoulder. My right shoulder is not working fine, but when I was younger, it was. And your hip joint. What do you mean? If this is the X, and that's the Y, and that's the Z, I say, of course, it cannot move in any direction. So I should have, notice, I don't care if I draw the arrow out or in. As we said, the sense is irrelevant here. You will get the negative answer if you do it backwards. You have RY and you have RZ. So it's three components. You say, how about the moments? No, there is a small ball here. That's what we call it, the ball and socket. It's like your shoulder. If this is the X, I can rotate about the X. If this is the Y, I can rotate about the Y. And if this is the Z, I can rotate around about the Z. So you can rotate this in any direction, way, shape, or form you want. There are no moments. Okay? If we move down here, we call that a journal bearing. And again, if this is the X, this is the Y, and this is the Z, notice that you cannot move along the X or the Z, but if you push this pipe, it's in a circular hole, so it can slide. So really, we have, force-wise, we have two reactions. We have Rx and we have Rz. How about the moments? Well, this thing rotates about the Y. So there is no restriction of the moment about the Y. But this thing cannot rotate about the X or about the Z. You see that? Cannot rotate about this axis or that axis. So therefore, there would be a moment about the X and a moment about the Z. And I draw it like counterclockwise, so you know we assume it's positive. Some people would write two arrows, maybe with a different color. So two arrows means moment, one arrow means force. A very similar one to that is if I make, I make the tube or the pipe that goes through this hole of the journal bearing, I make it thick inside so that it doesn't allow motion. And in that case, for a thrust bearing, we call it a thrust bearing. If the pipe cannot move along the Y, we add RY. But it still can rotate. It doesn't prevent rotation about the Y. So it will get 5 support reactions. 1, 2, 3, 4, and the thrust would make it 5. If it's a journal bearing, it's 4. If it's a thrust bearing, it's 5. Okay? Now we move to the hinge. And you have hinges, of course, in your house, everywhere. If you have a small, like cupboard or, stuff that you bought and attach yourself, you can have, of course, this thing. You see that um, basically it prevents motion in 3 directions. So I will have an Rx, I will have an Ry, and I will have an Rz. Of course, these are like 2 pieces that go inside. So for example, the top piece here at the bottom it will have something like a pin, and then the other side will have here a hole. And this pin goes into that hole. So in one direction, if I push it in this direction, it moves, but if I push it in the other direction, it doesn't move. So usually I have two hinges next to each other. Maybe the pin on this one is to the right, the pin on the other one is to the left. So you cannot move it in either direction, because if they are in the same direction and you push sideways, they will separate. So that's why we have three component of the force. How about the rotation? Of course, this thing opens and closes. That's how you attach it, and you open the door or the close of your cupboard. Uh, but it's it can rotate about the y. So there is no moments about the y. And you say, is there moments? Yeah, this prevents rotation in this direction and in that direction. However, I want to tell you is that when we design a hinge, we don't expect you to try to turn it around the z or the x. These are very small moments, and usually they are due to misalignment. Meaning, no matter how good you want to make this flush with, say, with the back of the cupboard or both hinges, they will never be exactly flush or exactly linear, unless you get the laser and you want to make sure that it's exactly aligned. And then when you open the door hard enough, you will mess it up. So these two moments are usually very small moments. So we say there are five unknowns, but we don't design the hinge to support moments about the z or the x. It's usually, if it in a utopian world, these would be three unknowns, exactly like the ball and socket. However, we add these two to make sure that, okay, it can take some of the misalignment. So don't worry much about that. But in this course, we will assume it has five unknowns. And if the problem wants you to use only three, it will tell you that the hinge has been aligned properly aligned. Properly aligned meaning you won't get these two moments. So it's another way of saying, treat it as if it were a thrust bearing. But we want to see if you understand that or not. Okay, so um, even if you think about it, even these two moments, but these, well, again, you can think of them as due to misalignment, or just, they prevent rotation anyway. But for the hinge, sometimes in many problems, you will see this term, the hinges have been properly aligned, meaning ignore the moments. So that's the translation from engineering to English. And then finally, you may have, say, a pipe, and that pipe, or it doesn't have to be a pipe, but something that is really fixed to the floor, a fixed support. A fixed support has six unknowns. It prevents motion in all three directions. It prevents rotation in all three directions. So you get six unknowns. And as I said, if that's a beam, we call it a cantilever beam. A cantilever beam is fully supported. It doesn't need anything else with it. If you use something else, like a cable or something, you make it statically indeterminate. I hope this was easy. I wanted a short session before I go into problems so that it doesn't take much longer when we solve problems. I will have a session right now. In fact, I'm going to tape it, where I will get you a couple of examples to go over. So hope to see you then. Thanks. Have a nice day.